physicists unravel the mystery of electrical conductivity disappearance. In the enigmatic world of quantum physics, scientists often find themselves in a predicament when confronted with phenomena that defy conventional explanations. It's not uncommon for them to stumble upon solutions serendipitously, as they initially dismiss peculiar signals as erroneous. This was the case when researchers encountered a peculiar behavior in a material's electrical conductivity. The phenomenon in question involved a material that initially exhibited conductive properties, but suddenly lost its ability to conduct electricity. While physicists suspected electrons were involved, the underlying mechanism remained elusive. However, a groundbreaking study published in Physical Review Letters has shed light on the culprits behind this mysterious disappearance act, Polarons, a unique amalgamation of particles. These polarons create a fascinating dance between the electrons and the surrounding atoms, ultimately obstructing the flow of electricity. This discovery marks the first instance of polarons being identified within a compound composed of thulium, selenium, and tellurium, rare earth metals integral to the development of cutting-edge technologies. Kai Rosnagel, the senior author of the study and a scientist at the DESY Institute in Germany, expressed his excitement, stating that the successful visualization of polarons in this context opens up new avenues for exploring the quantum cosmos of materials. Quasiparticles, a broader category to which polarons belong, describe the collective behavior of particles under specific conditions, akin to a single particle. In this instance, polarons illustrate the intricate interaction between electrons and the rare metal compounds atoms. The researchers emphasized that the properties of materials cannot be solely attributed to their chemical composition. Electrons, they explained, are influenced by the movements of neighboring electrons and tend to form quasiparticles, resulting in the emergence of novel particle-like states with distinct properties. This discovery was initially prompted by a seemingly insignificant bump observed during measurements of the thulium-based compound. The research team initially attributed the bump to technical errors, but its persistence across various measurements prompted a more in-depth investigation. It was only when they incorporated a 70-year-old theoretical model that the calculations aligned perfectly. The bump, it turned out, was the result of electrons interacting with the metal compounds atoms as polarons, according to the study. Chol-hee Minot, the lead author and a physicist at Kiel University in Germany, highlighted the significance of this discovery, stating that the inclusion of this interaction in the calculations resolved the discrepancies between simulations and measurements. The study's findings have broader implications, as physicists are already aware of similar properties in modern quantum materials. By harnessing these unique electronic characteristics, polarons could potentially accelerate the development of advanced materials, such as room-temperature superconductors.